Okay, hello everybody. Thank you for joining us. We will start this webinar very soon. We will wait a couple of minutes so more people could join us. So we'll start soon.
Let's start.
Okay. Well, welcome everybody. Hello, my name is Juan Ignacio Sapia, and I'm in charge of digital communication at ProCycla. In a few moments, we will start with the webinar Fundamentals of Computational Fluid Dynamics Modeling Focus on Bioprocesses. This webinar will be presented by my colleagues at ProCycla, Andrés Donoso Bravo and Constanza Sadino Riquelme. I will briefly introduce both of them. Andrés Donoso Bravo is a biochemical engineer and PhD in engineering science from Catholic University of Valparaíso, Chile. Constanza Sadino Riquelme is a biotechnology engineer from the University of Chile and PhD in chemical engineer from the University of Alberta in Canada. Both of them have extensive experience in process modeling and simulation, so we hope this webinar will be very useful for all of you. Okay, before we start this webinar, I'm going to give you a brief introduction about ProCycla so you can get to know us a little better. ProCycla is a company founded in 2008, based in Santiago de Chile, and with offices in Barcelona, Spain. ProCycla is specialized in agro-industrial engineer, consulting, and environmental technology. We have a strong focus on waste management and treatment. We drive circular economy and climate change solutions through research and development. We also offer biotechnological and advanced engineering tools for the transformation of organic waste into renewable resources and energy. If you want to learn more about ProCycla services, you can visit the company website, procycla.com. Okay, and before we start, we will show you on screen a series of instructions so that can you ask questions in the session and interact with the speakers. We will have 3 question turns during this session of about 10 minutes each turn. On the right panel of your screen that is showing now, you can see that there are 3 icons. The first one is for messages. It's the general chat where you can leave technical questions or questions about the webinar. The second one, where you can see the Q&A, is for questions. This is where you can leave your question for the speakers and interact with them. These questions that you will ask will be projected on screen, and we will answer them in order of arrival. Also, we will be launching service to better understand your interest and guide us through your questions and queries. You will find the pool in this third button of the bars you see on the screen. There you will be able to vote and leave your answers. Okay, and finally, if you have any technical problem, please write it down in the general chat and we can answer you with a private message and try to help you. Okay, thank you all very much, and we can start this webinar.
Thank you, Juan Ignacio, for your kind introduction. Thank you, everybody, for attending this webinar. I hope you will enjoy it. And so first off, a few words about this team. The name of the team is ModSim, Modeling and Simulation. So we basically try to face the challenges that the industry is is facing right now, especially regarding circular economy and the moving toward fighting climate change. And we do this by exploring mathematical modeling-based virtual prototypes. So thanks to the advance in computational and numerics, we are able now to try to create virtual prototypes based on models to try to address these issues at the industry level. So in regards to the content of this webinar, the webinar is broken down in 5 sections, as you can see there. We will start off with an introduction about the main concepts surrounding the modeling, CFD modeling. From section 2 onwards, my colleague Constanza Sadino will take over, and she will explain to you the CFD principles, followed by how to prepare the virtual prototype, which are the software that are available to be used, and the last section is we will show you some study cases that you may find interesting. So we will start with the introduction. So, a few words about mathematical modeling. I think it's worth laying out a definition of a mathematical modeling. Personally, the one that I like the most is like the one that Aikoff stated back in the days, that modeling is a representation of the essential aspect of an existing system. And this representation has knowledge that can be used. So it's a representation that has certain insight that we can exploit, we can use. So that's a pretty straightforward definition that I like. In any case, it's always going to be an abstraction of the reality. It doesn't represent the reality, the system as such, but part of it. And so it's going to be an abstraction, basically because it contains assumptions that will lead us to have some simplification or modification of our model. Then you have the famous phrase that essentially all models are wrong, because it's true, all models are wrong, but some of them are useful. So this is a quote by George Box. And so I think one of the clearest examples of this phrase is the famous ideal gas law that we all know, which is wrong because it's an abstraction of reality, but it's useful. We have all used this equation during our studies, and we still use it for process design. So that's a main example of what we just said. In simulation, which is another concept that we often use related to modeling, we can say that it's basically the exploitation of that model, of the created or taken model. So we can do modeling without simulation, but on the other hand, we cannot do simulation without modeling. So this is a little bit of putting some concept there so that we can have a common base moving forward during this webinar. In regard to about models, we can say that in general we have 2 type of models: phenomenological, which are based on data. We use data to create these models, and we have mechanistic models, which are based on the principles of the process that govern a certain system. So phenomenological models, we're not going to talk about that today, but there are several approaches there that are very popular now, with machine learning, deep learning, decision trees, several statistical approaches, you name it, plenty of. So that will be worth of a different webinar. So in terms of mechanistic models, we can say that there are 3 types of mechanistic model: the one that are based on algebraic equations, ordinary differential equation, or partial differential equations. But at the end of the day, you're always going to have kind of like hybrid models. You're going to take some mechanistic principles, some phenomenological ones as well. So it's always going to be a balance of different approaches. It's not common to have a pure mechanistic or a pure phenomenological model. But so those are the type of models that are there. In terms of mechanistic models, that are the one that CFD use, we can have algebraic equations, for instance, for very specific process conditions. For instance, for a steady state, if we have an equilibrium in our system, in our bioreactor, we can say that things are not changing during time, and we can have an algebraic equation in this case for the biomass as a function of the inlet flow or the dilution rate. So we have a mechanistic equation, a mechanistic model represented by this algebraic equation for a very specific reactor condition, a steady state that we all know that is very difficult to achieve. Then if we want to consider the transient period of the reactor, not only the steady state, we have to move to ordinary differential equations with this form, which is derivative. So in this case, with ordinary differential equation, most of the time we are going to be considering homogeneity, which means that the components of the model are the same regardless the position inside the reactor. So, and then we can have this kind of typical graph where we plot the different variables in time, and we have different curves and predictions, right? And then if we want to consider the heterogeneity of the system, so which means not only time dependence, also the spatial variation of the components of my model, then we have to work with partial differential equations. So we will have to solve different PDE systems, and most of the time we're going to be looking at working with the Navier-Stokes equation for momentum and other fundamentals equation as well. We're going to be getting this kind of nice graph, 3 on 2 dimensions. So we are getting closer to the physical system. So the complex we get, the more computational cost that we are going to be facing. So Constanza will talk about that in a little bit. So the last part of this introduction, it's about a concept that it's also very popular right now, digital twins. I think we have all heard it, at least. So we kind of like have an idea of what a digital twin it's about. So we can have, it's kind of like an hologram or a virtual representation of a system. And in this case, you can see like a tube with a turbine. So in terms of the uses of this word, if we look at the databases, this graph was constructed using Scopus. We can see that 5 years ago, it was barely used in the scientific literature. You can find less than 5 documents per year where this term was used. Moving toward the beginning of 2010, 2014, you can find around 10 documents per year in the world about which this concept can be found. But in the last 5 years, you can see that the use of this word has skyrocketed, kind of like an infection disease curve there. So this exponential growth will always lead you to think, well, is it a buzzword? Is just a trend, or is an actual concept that it's really kind of like gaining grounds in the scientific world? Well, in my opinion, the thing is, in many cases, there is not a clear distinction between a model and a digital twin. So if a digital twin is a model, so we've been modeling for hundreds of years, so digital twins exist long ago. But if you take If you analyze the literature and the different definition, we can say that at least a digital twin will have to comprise three things: the model of an object, so the representation of this prototype, so that you can work on the design of it, a set of data that is dynamic in time, and at the same time, you can use this data to adjust and modify the model accordingly. I think with those three things, we can say that we are working with a digital twin. So I recommend this paper here that you can consult. These guys they put a nice discussion about the use of the digital twin concept. So now I will leave the screen to my colleague Constanza Sadino, who is gonna talk about the next sections of the webinar. So please, Constanza, I'm gonna stop sharing the screen.
Can you see the presentation? Okay.
Yes.
Thank you, Andrés, for the introduction. So now we are going to delve into the fundamentals of CFD. So the initial CFD stands for Computational Fluid Dynamics. This is an advanced modeling approach that we can use to analyze and to predict the behavior of a physical system with fluids. Fluids can be gas or liquid. Okay, so to apply CFD, first we need to represent the physical system using the transport phenomena equations. Okay, these equations represent the balance of mass, momentum, and energy, and how they change in time and in space. These equations need to be discretized to solve them, so we use numerical methods. We can use finite elements, finite volumes, or finite differences. So we need the discretization of the space and the time, in the case we have a transient model, to solve the equations. And because we have a huge system that is very complex, so we have several equations. They are solved using algorithms that are implemented in computational systems. So we could solve a model in our personal laptop, or in the case that the model is too complex, we may need a high a cluster or another high computational system. In the process of abstraction from the physical system to the CFD model, we will apply simplifications and assumptions that are going to add error to the final simulation. Okay, so we have the modeling errors. So let's say we are modeling a tank, and we are focused on the impeller movement, but we know the tank has a heating jacket. But we are going to assume that the temperature is constant and uniform. So that's our first assumption. Then we have the first error. Okay. Then we are going to discretize the system, so we have the error that will depend on the numerical method that we are using. And finally, we have the solution error that will depend on the solver that we are using to solve the simulation. All these errors, we cannot avoid them. So we have to try to minimize them. Okay, and when we minimize an error, we are increasing the computational cost. So when we set up a simulation and when we solve it, we will always be dealing with the trade-off between accuracy and computational cost. So we will have now the first survey.
Okay, I'm gonna push it. It's charging. Yes, I'm doing this. Okay.
We would like you to answer this question. Do you know of any process or system that could be modeled by CFD? So we invite you to answer this question. So if you knew about CFD before this webinar, if this is something new for you. Okay. Thank you, Juan Ignacio. Okay, so I think I need to share the screen again.
Yeah, I
Okay.
think.
Um, can you see the presentation?
Yeah, it's available.
Thank you. So now that we know what is CFD, we are going to learn a little bit about how to prepare the build for prototype step by step. So here we have an overview of the workflow that we need to follow to build the CFD model. So first we have the pre-processing state, where we will abstract from the physical system to the model. So we will need to have the virtual representation of the domain. We need to discretize this domain, and we need to translate the phenomena that we want to represent into the equations. Later, we have the solution. So in this stage, we will need to choose the solvers that we are going to use, and we need to define which variables we are going to uh, follow up in order to assess the model. Next, we have the post-processing stage. It involves the analysis and the visualization of the results. And finally, we have the verification and validation, that it involves the assessment of the model. So we will check if the model is actually representing the phenomena that we want to model, and if it is represented at the level that we want. So we are going to explain in detail each of these stages with examples. So first, I'm going to contextualize the examples. So let's say that we want to model a fermentation that is working in batch mode in a mechanical mixing tank. Okay, so what is what do we have in this process? The biomass growth. As the biomass growth, metabolites are secreted, and the metabolites are accumulated in the culture medium, and this changes the apparent viscosity of the fluid. The fluid becomes more viscous, so the mass and heat transfer is impaired, undermining the yield of the fermentation. So let's see these videos. So here we have an example of a fermentation that changed from Newtonian water-like to non-Newtonian pseudoplastic with a higher viscosity than water, and we can see how the flow changed close to the walls. So the idea is to use CFD to gather more information and to understand how it is changing the fluid dynamics of the tank. So because we cannot model exactly the kinetics and the whole fermentation, we apply a more simplified strategy. So we use three fluids to represent the fluid dynamics of three different stages of the fermentation. So we can use, for example, water to represent the fluid dynamics of the system at the beginning of the fermentation, and we can use two non-Newtonian fluids to represent the intermediate and final stages of the fermentation. So these solutions, solution A has a higher viscosity than the other solutions under the same operating conditions. Also, if we use this approach, this strategy of using abiotic fluids to mimic the fluid dynamics of the fermentation, we have some advantages. So, for example, we can isolate the effect of the impeller mixing from the effect of the aeration, so we can understand how they interact. To measure the effect of the viscosity on the fluid dynamics, we measure the torque on the impeller, So this is the main variable that we use to validate the model. And we will know what is the validation later. So let's see how we start the pre-processing stage. So if we have this tank, okay, we need to have a virtual representation of this tank. So the first thing that we could do is to build this geometry, okay, this through computer-aided design. However, this domain is not useful for CFD because CFD uses the domain, the volume that the fluid is using. So, for example, we don't need the external structural support. So, what we need is the volume of the fluid. Okay. Also, we have to consider the simplification of the geometry. There are small details that we can delete from the domain and that will not affect the fluid dynamics. So, for example, we don't need to model the screws. Also, we need to think how we are going to represent the phenomena that we want to model. So, in this case, to model the movement of the impellers, we need to divide the domain, the geometry, with these cylinders around the impellers in order to be able to set up the reference frame for the movement. Okay, and also we may need to divide the geometry further in order to improve the quality of the mesh. Okay, so when we are simplifying the geometry, we always have to ask ourselves how this is going to affect the fluid dynamics. So let's say we have the tank, and the tank has 3 probes inside to measure temperature, pH, and other variables. So we could build the geometry without the probes or with the probes. Okay, so how this could change the output of the simulation? If we see at these velocity contours that you have in the right of the slide, the velocity changes when we add the probes. So we have to consider what is the purpose of the model in order to conclude if this simplification could change the conclusions or not of the final result. Okay, so there is not like a correct or incorrect answer here. It's just what is the purpose of your model is what you can do, and without affecting the final results. Once we have the geometry, we need to discretize the geometry. That means we need to divide it into small cells. So here we have 2 different meshes of the same geometry. The first one has only tetrahedrons, and the second one has tetrahedrons and hexahedrons. So if we have an irregular geometry, tetrahedrons will be the easier and faster way to mesh the geometry, but tetrahedrons add numerical diffusion. What means a numerical diffusion? It smooths the gradients artificially, so we have a less accurate result. On the other hand, the hexahedrons, they are more accurate. Like they can give us a more accurate result, okay? But because the geometry is not regular, it may be very difficult to implement hexahedrons, for example, close to the impellers. So here what we did was to divide the geometry into the regular zones where we could implement hexahedrons, and we have the zone of the impellers where we have the tetrahedrons. And you can see here that we have a very fine mesh close to the impellers because this way we are reducing the effect of the numerical diffusion. Okay, so we will need to refine. That means we will have a higher cost to be able to have an accurate solution. close to the impellers. So here we have a survey. Um, um, so the second survey.
Okay, I'm launching it. I'm publishing it. Okay.
So we invite you to answer this question. Do you have any experience using the Cfde tool? So you can answer that. You have used Cfde before? You haven't? So thank you for your participation. Now we will continue with the presentation. Can you confirm if you can see the slides, please?
Yeah, it's available.
Okay, thank you. So now we have the geometry and we have the mesh, we need to define the models that are going to represent the phenomena that we want to study. So we need to characterize the system. How is the flow regime, which type of fluid we are working with, how many phases we have, do we want to model the species transport, do we want to model the temperature, or we want to see this as the stationary state, or we want the transient state. All these things are going to define the model, the final model that we are going to simulate. So let's see how we choose this. So we'll have some criteria that will be based on the physics of the system. So for example, if the system is laminar or turbulent, that will depend on the Reynolds number of the system. Let's say that the system is turbulent, then we will have to use other criteria to choose the proper model. So depending on the complexity of the system, if it is too complex, we will prefer to choose a model that will help us to stabilize the solution. So we will use K epsilon. But maybe we want to model the eddies, how they form and how they dissipate in the system. So in that case, we need more accuracy on the result, and we could try with LES. However, this model is very expensive computationally, and maybe we don't have the resources, the computer that would be required to solve LES. So maybe we could choose a more middle ground model like Reynolds stress model. So this is the kind of criteria that we have to use many times to find the balance between accuracy and computational cost based on the goal of the final model. Here we have an example of the effect of the turbulence model on the solution. So if you remember, we measured the impeller torque for the mixing tank. So here we have the simulated torque, and we have the value for two turbulence models. So we have the K epsilon model and the SST K omega model. For SST K omega model, we can see more oscillations, and more oscillations than for K epsilon, and that is because of the nature of K epsilon. It adds a lot of artificial diffusion to the solution, so it smoothes the gradients. So we could expect this kind of differences when we compare these two models. It is not that one model is right and the other one is wrong. It will depend on the purpose of your simulation, which one you will use, and also it will depend on the computational resources that we have to solve the simulation. In another example, for example, if we want to simulate a multiphase system, okay, we will have different options, and we will have to choose based on this same criteria. So complexity of the system, what is the goal of my simulation, and how much resources I have to solve. So if we have the tank and we include the headspace, if we use the Eulerian model, we will be able to predict a very sharp interface. But with the mixture model, uh, if we simulate the same conditions, we will have a blur interface. So probably we could think, just looking at this, that Eulerian is the best option. However, the Eulerian model is more unstable. So uh, the velocity magnitude that it predicts significantly over predict the velocity in some points. So we would expect to have the maximum velocity close to the impeller tip, and in this case it would be around 2 meters per second, so you have an idea. But here the maximum velocity reaches like 20 meters per second, which is significantly higher than the maximum that we were expecting to get. So in this case, because of the numerical instability of the Eulerian model, we have to keep working with the mixture model. In another example, so if we want to model the mechanical mixing of the tank, we will have two approaches that we can use. The multiple reference frame, okay, that this approach fixes the impeller, okay, and predicts average velocity values of the fluid moving around the impeller in a fixed position. And we have the sliding mesh that actually moves the impeller. It you can see that it changes the position in time, so it can capture the real transient behavior uh, and transient changes of the velocity that is triggered by the impeller movement. So if we see this in a graph, for a point that is close to the impeller, that is 0.7, MR multiple reference frame predicts a constant value, while the sliding mesh is able to capture the periodic oscillations that are triggered by the passage of the blades. Um, uh, if we have a point that is more close to the walls, here we see that the oscillations are not as big as 4.7, but we can see that still we can capture some oscillations that multiple reference frame is not able to capture. So we have to take this into account when we choose the model, always having in mind what is the purpose of the model, what we want to study. So if we choose one or other model, we will have to know how it's going to affect in my final conclusion. Once we have the models, that means we have the equations, we need to define the boundary and initial conditions that will allow us to solve the system of equations. For that, we need information such as here, for example, the tank. It is closed or it is open. So if it's closed, we will have no slip condition, which means that the liquid is touching the cover, and so at that point it's not moving. If it is open, then we have somehow an interaction with air, so the air is not impairing the movement of water, so water moves free. Those conditions are different, so we will have a different solution depending on which one we use. Also, we have to define the initial condition. So is the system initially at rest? Or also, if my system is unstable, like if the models that I choose are unstable, maybe I should select an initial condition that is going to help me to stabilize the solution first. All those things we have to take into account when we are pre-processing the model. So with this, we have finished the first section of the webinar. So we will go with the first round of questions.
Okay. remember to write your questions on your in the menu that of the button that have a Q&A. In that button, you can leave your questions for Constanza and Andrés. If you have any problem with this menu, you can ask in the other menu. Well, okay, we have one. Perfect. So, MK Valdenito asked if can CFD be used to monitor liquid waste treatment or sewage treatment processes?
So CFD can be used to simulate wastewater treatment or sewage treatment, but for monitoring processes, it may be not very suitable because as it is very expensive computationally, if you want to have something like in real time, it may be not very helpful because it's going to take long time to get the results. But for design and for optimization purposes, it is very helpful.
Okay, so I mark it as answered. And we have another question here.
If I can translate it if you want.
Yeah.
So, which kind of like criteria you use to decide until which point you want to get a more complicated model to get a more accurate answer?
So, well, first, it will depend on the resources that you have to solve the model. If you're using your personal laptop or a cluster, then you will have different limitations. Also, the time. Like, if you have, if you can wait for 12 months or for 1 month, then that will also put a limit on the complexity of the model. Also, you have to take into account what you are going to use the model for, and also the the level of accuracy that you have uh, for the experiments, because you will need to validate the model. We will see that in the next sections, and the validation is against experimental data. So you know that we always have error in the experimental data. So we cannot validate the model with a higher accuracy than the accuracy of the experimental data. So until what point we will have the complexity of the model, that depends on many factors. So that's why you have always to have in mind what is the purpose of the model, what do you want to know, and do you need that much accuracy for the purpose of the model. If it's like if you are modeling a rocket to send to the moon, probably you will need very high accuracy, right? And so you can afford a year of simulation. If you are modeling a tank, you don't need that much accuracy.
Yeah, I agree with Connie. At the end of the day, it's the goal. The goal. Why you are using CFD, and then you will have to choose a certain complexity, and it's always going to be a trade-off between resources, skills, time, money, and so it's about the goal, and then what it's around the execution of that modeling work. I think we also have a question in the chat. Someone asked, "What software do you use?" I've
Yeah.
used CFX and Fluent. Um,
Yes, we have used Fluent as well, and we use OpenFOAM. It's an open source software. We will talk more about that later. Um,
Good.
Okay,
So
Let's move on then.
we'll go on. Perfect.
okay, can you see my screen, my slides?
Yeah.
Thank you.
Can
So
you press hide the bar that it's at the bottom? Is is it? Yeah. There you go.
better. Okay.
Better.
Okay. So once we have the pre-processing stage ready, we can solve the model. How we do that? So we need to use the solvers. So the continuity equation of transport phenomena has the density as a variable. Cfd couples the 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 density and the velocity, sorry, that is in the continuity equation with the pressure. Okay, and for that we have to select the solver. If we want to have a cheaper choice, we could use simple. But for simple, we will have to use, if we have a transient simulation, we will have to use a finer time step than if we use PISO, for example. So again, is a trade-off between accuracy and the computational cost that we can afford. Um, Also, the discretization methods, we can use first order, that is going to be faster and easier to stabilize, but is less accurate. Or we could use second or higher order, that it may take longer to stabilize and to finish the simulation, but is more accurate. So, as I have said before, it's always this trade-off between accuracy and computational cost, and also the stability of the simulation. When we are solving the system of equations, uh, numerically, we have a set of iterations. To measure the convergence of the iterations, we have to follow up the residuals. Okay, so there are some ideal values that we should expect to have. So below 10 to the power of -3 is like the ideal for engineering purposes, but if we can have a solution that is below 10 to the power of -5, is better. Like, and for purposes of publication, like to have an article in a journal, probably you will be asked to have a residual below this value. Even if we have very small residuals, the solution may be unstable. So we have to check other variables that are critical for the model. For example, in the case of the tank with the mechanical mixing, we need to monitor the velocity. And depending on how that velocity is behaving, we can identify if we have some numerical instability. And we have to take into account if we are expecting a solution that is stationary or periodic. We have to take into account which values have a physical meaning for our system. And if we see discontinuities, if we see jumps in the values, then probably we have a numerical situation. And we need to improve the models, choose another model that is more stable. So here we have another survey. So
Okay.
Juan Ignacio,
Introduction.
you can.
Uh, it's already published, right?
Okay.
Right now. Okay.
So are you interested in training this type of modeling? Would you like to learn how to implement a CFD model? We invite you to answer this question. So yes, everyone that
Okay.
answered the survey, yeah, agrees that they would like to learn more about CFD.
Perfect.
So let's continue. So we did the pre-processing state, we solved the model, now we have the results, so we have to analyze them and visualize them. So what kind of variables we can analyze? We have several variables, as you can see here in this list. And which one we want to analyze? Well, that will depend on many criteria. So first, what is the purpose of your study? What experimental or analytical information do you have? So if you have information about the velocity, then probably you want to plot the velocity and compare the experimental versus the simulated values. Um, what do you need? You need the information for a point, for an area. For example, you want the concentration of certain species at the outflow of your system, or you want a volume value. Do you want to see the changes of these variables in time? All these things we have to have in mind um, when we are setting up the model to be able to analyze them at the end. How we can visualize this information? So here we have different graphs with the same variable, that is velocity. So we have contour plots where we can see the gradients of velocity close to the impellers. We have vector plots that could help us to understand the interaction between the impeller compartments. We also have this graph that is showing how the velocity changes in time. And finally, we have some three-dimensional visualization. Well, this case is a bit different. Here we have a bus, and here we are visualizing the air vortices that are formed in the back of the back end of the bus. And for that, we use streamlines. So as you see, we have uh, many options to visualize the result, and that's one of the strengths of Cfde, that allows us to see our system from a different perspective. Finally, we need to go through verification and validation. So what is verification? So if you remember, we use a discretization to solve the system of equations. So the level of the discretization, how small is the cell that we are using, is going to affect the result. So we need to assess if we are using a cell that is fine enough to capture all the phenomena that um, that is inside our system. So for that, we will use different meshes that they are going to be similar in the sense that if you have a refinement around the impeller, the three of them are going to have the same zone with a refinement, but we will have a coarse mesh, medium mesh, a fine mesh. So what is the purpose of this? If the coarse mesh has the same result than the fine mesh, it means that the coarse mesh is fine enough to have to simulate a result that is not affected by the discretization. Okay. The same if we have a transient simulation. When we choose the time step has to be fine enough to capture all the phenomena that we have in the system. If we have this condition, then our core mesh is independent from the discretization. Okay, so the idea is to have a fine mesh that is able to capture everything, but that fine mesh has to be as much coarse as we can in order to save computational resources. When we have the verification done, we have to assess the model to check if we are predicting, if we are modeling the physical system properly. For that, we can use different variables. So the ideal variable is a global one that with one parameter you capture the fluid dynamics of the whole system. So for example, torque. Torque is able to capture the effect of the viscosity with just one parameter, but with the effect of the viscosity in the entire system. Okay, if you use a local variable, for example, velocity, you will need profiles. Okay, because if you use just the information on one point, then it's not very um, it doesn't have enough information to validate the system, so you will need profiles like we have here. So these are radial velocities in the axial component at different positions of the tank, and we can see how the model is able to capture the same behavior that we are able to capture experimentally. Here it's very important to say that most of the time it's very difficult to collect the experimental data to perform validation. So it's very common to use borrowed data. So in that case, you have to be very careful to use data that comes from a system that has similarities with your system. So for example, if the system is turbulent, you probably want to use data that comes from a turbulent system. Um, and if your system has two impellers, probably you want to use data that comes from a system that has the same number of impellers and that has some spacing that is similar. Because if we have different geometries, then the comparison, the purpose of the comparison is lost. Um, Also, well, here we have the torque for the three abiotic system that we use to mimic the evolution of the fermentation, and we have the simulation of the three systems. If we zoom, here we can see how uh, the effect of the viscosity was captured by the torque. Okay, so as higher the viscosity, here we had a bigger torque. And the simulation was able to capture that. So the continuous line is the simulation, the dashed line is the experiment, and we can see how the CFD model is able to capture the effect of the rheological changes that affect the viscosity in the system. There are some parameters that you can calculate to have a final validation. That's beyond the scope of the webinar, so we left you here the name of the paper that you can read in case you want to know more about this. So we are in the second round of questions.
Right. We have a question by Javier Saleh. I join it. Okay. I didn't understand how to represent the movement of structures in the geometry.
Okay, so in the case of the tank, you have to define a cylinder that is surrounding the impellers. So what you will be modeling actually is the movement of the cylinder, because you will change the, the reference of the movement. So you will use the cylinder as reference for the steering of the blades, and you can then use two approaches. You can use a steady state approach, so the impeller will be fixed and you will have like kind of an average velocity. And also you can use a transient approach where you actually will see the movement of the impellers and will see the effect of the passage of the blades, how the velocity changes in time. It's a bit complex, but the main idea is that the reference of the movement is changed. So the equations include a different velocity for the movement of the impellers.
So another question by Javier: how can I use the concept of digital twins in a CFD simulations?
So CFD models are kind of the more accurate models that we can have of a system, because we can model, we can simulate the changes in time and in space. So the CFD models are the more accurate approach that we can have to our system. So that's why we call it digital twins, because we are replicating the system, and we are replicating it in the more accurate way. So um, somehow we are copying what is happening in reality. We have a copy of that in the computer, so we can experiment with that, and we can optimize the system from the virtual perspective, and then move it to the real system.
Perfect. So I mark it as answered. Okay, let's wait a few seconds if there are any more questions.
I would say let's continue because of time.
Okay, perfect.
We have a certain time frame, right?
Okay.
There will be another section of questions at the end.
Yeah.
Right. Yeah.
Okay. So now we know how to prepare a CFD model, and we need to know which softwares we can use. So we have commercial softwares, and we have free and open source softwares. The free and open source softwares are mostly focused on certain tasks of the workflow to implement a CFD model. So if we use open source software, we may need to use different software for each state. So we could use one for the geometry, one for the mesh, one for the resolution, and then another one for the visualization. So here we have uh, how looks like Blender. So you can see here that Blender has a user-friendly interface, and here we are showing the geometry of a tank that we built with Blender. In the case of OpenFOAM that you can use to implement the mesh and to solve the system, it is less user-friendly because you're required to code the model. So you need to have some knowledge about some languages that you use for programming. But an advantage of that is you can change it as much as you want. It's very flexible, so that is really nice of this, is because all the users, they interchange codes, so you can find in the community codes for specific purposes that are there for you to use, and you can modify them. And we have ParaView that is also very user-friendly. With this, you can record videos, you can visualize the contours that I already showed you, and this will help you to have a better analysis of your data. In the case of the commercial softwares, they have tools for the task of all the stages. So, for example, ANSYS provides a software for the geometry, a software for the mesh, software for the solution, and a software for the post processing. And it's very user friendly. You can see here you have boxes, buttons, and you just press them, and you define your model. Because of that, because it's very easy to use, also it's very easy to abuse, as my my PhD supervisor says. It can be sometimes a a disadvantage because sometimes we don't know what we are pressing, we don't know what it means. So you have to be aware of what you are defining when you press a button. And also because of that, it is less flexible than OpenFOAM because you are not coding your model, you are just using the model that is already coded. So it's less flexible. Here we have a new survey.
Okay, I'm
We
publishing.
invite you
Yeah.
to answer, how do you rate the content of this webinar? So you like the quality of the content, you like the quality of the presentation. Okay, thank you for the participation. I'm going to continue with the presentation. Okay. So now let us see some study cases to see how we can use CFD on bioprocesses. Okay, so first we have the case of biopolymer production. So in this case, we have a tank. It has two impellers, and uh, during the process, the viscosity of the fermentation broth changes and it increases. So how that changes the fluid dynamics of the system? Here we can see, for example, we have the initial state of the process and the final state, and we can analyze how the impeller compartments are interacting, and we can see that the interaction changes. Here we see in the bottom differences between the impellers, and all these changes that we can identify could explain, for example, changes in the mixing time. So we could expect that close to the final stage of the fermentation, we will have higher mixing times because we have this flow pattern that is named parallel flow pattern, which means that the impellers are working independently from each other. So that means that we don't have much interchange of fluid between the compartments, so it takes longer to mix properly. Why is happening that? Why we have this kind of flow patterns and why they are changing? We can answer that looking at the vortex formations. Here we see the evolution of the vortex that we have around the axis of the impeller, and we can see that the vortex has a shape that changes as the viscosity of the fluid increases. And this shape of the vortex could explain the evolution of the interaction between the impellers. This vortex is also important because it's going to help us to avoid the sedimentation of particulate matter in the bottom of the tank. So here we can see uh, a swirl that is moving upwards. Okay, this phenomenon is called Ekman Layer, and it helps us to move the microorganisms that are in the bottom of the tank, move them upwards to keep the system well mixed. And we can see how this vortex changes as the viscosity increases. So we could expect that at the final stage of the fermentation, we will have a more significant sedimentation of particles, and therefore we'll have a system that is more poorly mixed. There are other vortices are very important. These are the trailing vortices. So they are formed behind the blades as the impeller moves. And here we can see okay, I think you should be able to see the videos. The trailing vortices are moving. And you can see that as the viscosity increases, the vortices are more short. Okay, so the length of the vortices changes and the area that they span is reduced. This means that the mixing is being impaired by the viscosity, because these trailing vortices are the actual responsibles of the mixing process. So as we have changes over the fermentation, uh, we can see that the trailing vortices are evolving as well. Finally, if we want to study the vortex formation in the surface of the liquid where it is interacting with the gas of the headspace, we can use a bigger domain to simulate it. Here you can see the vortex that is formed in the case of water and in the case of a pseudoplastic fluid with a higher viscosity. And we can see that the shape of the vortex is different. In the first case with water, we have a vortex that is touching the upper impeller, while in the second case, the vortex is not touching the same impeller. This could be very important in some cases, because there are systems where the mechanical mixing is actually used for the entrapment of air or another gas from the headspace. So with this kind of simulation, we can predict how well we are aerating the system, and we can see how well the model is predicting the experimental system. As we compare here with the experimental, with the photos of the experimental system, we can see that we actually were able to capture the shape of the vortex. These kind of simulations are computationally very expensive. What do I mean with that? This video with water represents a fraction of a second, but the production of the video took 4 days of simulation. It took a cluster. We used 96 CPUs, and we used almost half terabyte with data. Also, we can simulate the aeration. So here you can see the injection of air from the sparkle ring. And we can see how the interface changes due to the effect of the aeration. In another example, we have a wastewater treatment. So this is the anaerobic digester that ProCycla has designed. And we have used Cfde modeling to study the mixing of the system. So here we have the geometry of the system, and we have the mesh. On the mesh, you can see a mesh with hexahedrons. So we are trying to be very accurate with the result, and we are trying to keep the numerical diffusion very low. And with this model, we can study the volume fraction of gas. So how we can see when we recirculate the gas that we are producing, the gas is injected here close to the bottom of the tank, and we can see how it moves upwards. And in this process of moving upward, we can study the flow patterns that we get inside the system. Here I'm going to show you a video. So the surfaces that you see in this video are the interface between the liquid and the gas that we have in the system, and the color that you see here is the velocity. So blue means that is at rest, 0 velocity, and a more red color means a higher velocity. So I'm going to play the video. Not working. No. So here we can see the effect of the injection of gas on the surface of the liquid. We can see how the waves moves in the surface, and this is going to provide us very useful information to optimize the position of the gas injection. This video took almost 2 days of simulation, and you can see here that we have almost 70 seconds of process. It took 2 days of simulation. We use a computer with 8 CPUs, and we use a bit less data than in the previous video that I showed you. In a more simple example, we have this tank. Here we have water. Okay, this tank is closed, so it has a cover, and we have water almost touching the cover of the tank. We are somehow representing a water dispenser. So let us think of a water dispenser. What we expect to happen is that when we have an outflow of water, we have an inflow of air. So we have bubbles, okay, that use the space that the water left empty. And here in this simulation, we have exactly the same phenomena. So here we have an outlet, and as we simulate the outflow of water, we also have the inflow of air and the formation of bubbles that will move up to the liquid surface and will trigger the movement of the surface. So to conclude, there are some prospects for CFD. So CFD is very, very useful to complement the experimental research because there are several variables that we cannot study experimentally because it is too expensive, too difficult, too dangerous. So in those cases, CFD can help us to gain information. And particularly in the industry, CFD can be used to improve the design and optimization of the reactors and other equipments too. There are some challenges that remain to improve the CFD modeling. Particularly, we are working on coupling the fluid dynamics with the microbial kinetics to have a more integral CFD simulation. This is very challenging because fluid dynamics and the kinetics have very different time scales. So that's something that has to be solved. And also we need maybe to face that we have a very high computational cost if we want to simulate long-term processes. For instance, you already saw that to simulate a fraction of a second, it took almost 4 days. So what if we want to simulate a process that takes 72 hours? It would take us years. So there is still a challenge there. And we, as I said, we are working on the coupling of fluid dynamics with the microbial kinetics, and we are going to present a review in a congress very soon. So with this, we have finished the webinar, and we will have the third round of questions.
Yeah, let's proceed with the final questions. We have this one from Sebastián Guzmán. It says, I want to know if there are models that include pneumatic agitation by gas recirculation.
Yes, that's exactly what I showed you in the last examples. So in this long video, what we have is pneumatic agitation, and with gas recirculation. So you can have a multi-phase model to represent that.
Yeah. So I wanted to add something about this, and in regards to coding, when you use OpenFOAM, the free access software, it's true that you have to code more, but there's all this. You don't have to code the actual the whole equation from the scratch. There are solvers already there, ready to be used, that are, so it's already very well packaged. And the thing that you have to code, it's more or less the interaction between all the settings of the models, and that's something that you don't need to do when you use Fluent, for instance. But yeah, there is a big amount of solvers already programmed and verified in OpenFOAM, so that you can also get a hold on.
Okay, well, if anyone
I
has,
think there is another question.
yeah, I will join in stage. Let me copy it because it's in the other menu, so I will copy it and I will show it.
So,
I'm doing a Master of Engineer Sciences, and my thesis is about simulating an airlift reactor and validating it with the data of a reactor we have it in the lab. I will take a course of CFD the second semester. Wait, Gorina, thank you. Well, thank you for your
thank you.
participation.
So I will wanted to comment about another question. I think they posed. I think in the previous round it was a digital twin. So it's good to, when you have a project with industry, it's good to have a good control of the expectations. Sometimes people will imagine that it's easy just to get the virtual prototype of your process and run simulation and have hours and hours of simulated operation, and that could be true if the system is simple. It doesn't entail, for instance, many phases. If it's just water, if it has air, if it has solid, then you have multi-phase, then you are adding more complexity, and that will take more time to be solved. So CFD, I think, is the proper tool to create useful digital twins, but you will always have to see if what the industry needs, it's feasible to uh, to do through CFD modeling. So it's good to have a good a good, and put your feet back in the earth, and then see if what they want, it's actually doable or not with modeling.
Yes, it's true.
It's very
We have
computational.
another question.
Yeah. What are the advantages between MBF and MEF to know which one to choose according to the case of study?
Yeah, well, so when you are choosing the software, you are also choosing what numerical method you're going to use. So, for example, OpenFOAM and ANSYS Fluid, they use finite volume. Finite volume has the advantage of naturally preserve the balance of mass. So somehow it will help you to solve the transport phenomena equations. They have some difference. So some methods they use integral form, the other use derivative forms. But in this particular case, with finite volume, the form that it uses of the equations, it helps you with the balance of the equations. So yeah, I think that answers the question. If you have any other question, you can share it with us.
In the meantime, it's worth noting that this seminar, the recording, will be available on our YouTube channel. And also, I think there was one of the presenters, one of the attendees, that said that he was asking about this a Spanish version. There is a Spanish version of this webinar that it's going to be shared with you guys, so that you can also take a look at it.
Okay, well, thank you everybody to join us. Thank you, Constanza. Thank you, Andrés. And well, we'll see you next webinar.
Thank you all for
Thank you.
coming.
Goodbye, everybody.
Bye.